All right, guys. The video for today, I do apologize. I put a video up that was a couple of days or a couple weeks later from where you guys are, or at least a week. So there's a lot of information between now and then. I still am in Kitchener. I just wanted to fire a quick video off. I'm going to try doing it this way for this video. Let me know what your thoughts are on it. I don't know how legible I'm going to be able to write on this, but this is the style I'm going to use for right now. I wanted to get this video out just so that if you needed to or wanted to watch it tonight, you could, or at your leisure tomorrow. So without further ado, let's try working it out like this. I hope this ends up being legible for you. If not, I do apologize. From last class, what we had talked about, we had finished talking about our Y configuration. So that was our Y configuration, obviously shape of a Y. And then we had our delta configuration. And these could simulate a three-phase alternator or a three-phase transformer, or even a delta or Y three-phase load in the configuration that they're in or the way that they're drawn. There's a few things to remember. In Y, we saw that our I line was equal to our I phase, where in delta, our E line was equal to our E phase, or E line. So E phase is equal to E line. So very important to make the distinction between those two. And if we looked at voltage in Y, our E line is equal to our E phase times root 3. And in delta, we had our I line is equal to our I phase times root 3. So the two rules are flopped. And it is also important to make sure that you can go back and forth between the two rules fairly comfortably, because as we build on these circuits, we are going to have resistor or resistive, capacitive, and inductive loads, and you're going to have them in either a Y or a delta configuration. So let me just break this down a little bit further. So we had our Y configuration, and let's do a little bit of math. I want to show you how you end up breaking down delta and Y. If I were to give you, let's say that I had a phase voltage. So we have an E phase of 347 volts. And I'm going to say that I have a resistance, and this is going to be resistance per phase of, let's do 10 ohms per phase. So that 10 ohms per phase, that means that I have 10 ohms here, 10 ohms here, and 10 ohms here. So I'm going to be going back and forth between the stylus and my finger. I haven't really used it this way, so we'll see whatever works the easiest. And hopefully it's legible. Right now it kind of looks like an 8-year-old is writing this down, but we will see how everything works out at the end. So we have 10 ohms per phase with 347 volts per phase. If we were to take those values and were to go into our terminal values, so if we were going to look at our voltage between, let's say, line 2, line 3, or line 1, line 2, we would end up having to take that voltage of 347 volts, and we would have to multiply that by root 3. And as we talked about, that these two phases here are 120 degrees apart from each other, so they cannot be vectorially just added together, or just can't, take 347 plus 347, add them together, which would give you, what would that be, 700 or 694, but you would have to take them and add them vectorially based on them being 120 degrees apart. So 347 times root 3 is going to give you a value about 600 volts. So then that would tell me that my voltage at this point is 600 volts. And if I wanted to look at my individual phase values, let's say I wanted to calculate my current per phase. If you're doing your current per phase, I would be doing the math the exact same way I would do a regular series circuit. So if we just get that guy out of there. So Ohm's law, we know that obviously E is equal to I times R. And if I wanted to get I by itself, I would have to divide R out on each side, so we end up getting our current is equal to E divided by R. So we would get 347 volts. 347 divided by 10 ohms gives us a current of 34.7 amps. So each phase is going to see 37.4 or 34.7 amps, sorry. All right, so fairly straightforward. So you can calculate each phase like that. So we calculated our line voltage, we've calculated our phase voltage, we've calculated our phase current. And as we talked about, if I were to look at just this point right here, if I were to put an amp clamp around that coil, I would see that there would be 34.7 amps if I could put an amp clamp around it. And then if I came out into the line, we don't have multiple coils adding on or producing that current. So our current in the line would be the exact same as it would be per phase. The only thing remaining is to calculate what our power is. So you guys obviously remember or know how to calculate your power. Let's say it's a value in watts in a series circuit, and that is simply just your volts times your amps. And if we were to look at it just as a resistive circuit, obviously there's no power factor involved, so we don't have to worry about that if it's purely resistive. But we need to look at what the difference is between a single phase power supply and a three-phase power supply. So notice that if we were to calculate our power per phase, we would have 34.7 amps times 347 volts, and volts times amps will give us our wattage. So 34.7 times 347, that would give us a value of roughly 12.04 kilowatts. So that part of it's fairly straightforward. And if I'm calculating values out for power per phase, I have 12.04 kilowatts in phase number 1, 12.04 kilowatts in phase number 2, and 12.4 kilowatts in phase number 3. And to calculate our three-phase power, it is simply just taking those values. So you had a value of your E phase times your I phase. So that gave us this value of 12.04, and I just multiply that by 3 because I have 1, 2, 3 coils. So I would take that 12.04 kilowatts, multiply that by 3, and I get 36.123 kilowatts as our three-phase power. So that is if you're using phase values. You don't just have to use phase values, you can also use your line values. So if you're calculating out using line values, there is a little bit of a difference. Obviously, your line voltage is larger, root 3 larger, so it's 600 volts. And something interesting, so it's root 3 larger. I want you to show you, if you take your calculator and do root 3 times root 3, that gives you a value of 3, which is our value over here. So if you were to look at the difference between the two, obviously your three-phase power for a three-phase circuit, if you're calculating it as a phase using phase values or line values, that they should be equal. So I'm just going to rearrange this a little bit. And hopefully you can follow this. If I do E phase times root 3, you can agree that that is the same as just E line, right? And if I then multiply that by I line, and we know that in a Y configuration, or I phase and I line are the same. And now I just multiply this by I line. Mathematically, what is at this point the difference between this formula over here and this one over here? We had just talked about that root 3 times root 3 is equal to 3. We've only multiplied by 1 root 3 to find a line value. So if the difference between this formula right now and this formula right now is simply root 3 more, we can then add to this formula another root 3. And this is now, sorry, let's erase that and get that. This is now our formula using line values. E line times I line times root 3 is equal to our total three-phase power. So if I put these side by side, these two formulas are the same, or would give you an equivalent value. E phase times I phase times 3 is the exact same, or this is equal to E line times I line times root 3. So the only difference in that other root 3 is right now in my E line if I'm looking in a Y configuration. So those two formulas you need to remember in Y. And these are also the same formulas you're going to end up using in delta for calculating power. And then you just need to remember your rules for your Y configuration. So I'm going to erase this again. I'm now going to expand a little bit. We're actually going to put a load into the circuit. So I'm going to do a Y connected alternator. And I'll just put a little circle around it just to indicate it's an alternator. And I'm going to end up having a three-phase resistive. So this is going to be resistive load. Resistive. So I'm going to connect my, let's say it's, could be three-phase lighting. And we're going to say that this is 12 ohms per phase. And anytime, and I was saying before, we are always going to use balanced loads. I'll never have a time where they're not balanced. And we are going to have a supply voltage of 120 volts. And typically I could ask you to solve for this entire circuit. So this is your alternator over here. So first things first, I want to deal with my phase voltage of 120 volts. So that's my phase value, and I want to end up getting a line value. So to go from phase values to line values, remember we got to take our 120 volts and multiply that by root 3. And if we do that, we get a voltage of 208 volts. So we know that our line voltage is 208 volts. And I'll be erasing some of this as we go through, just so that we have room. One thing to keep in mind is that if you have a Y-connected alternator and then a Y-connected load, whatever the phase value is of the alternator for the voltage, your load phase voltage is going to be the exact same. So obviously we do know that once we come out into our line values, we are going to be root 3 larger. Once we get over to a load and we get to these 2 points here, our 208 volts is now going to be split between this coil and this coil. So those two resistances of that load are going to be splitting that 208 volts. And remember, they are not 180 degrees out of phase with each other. They're 120 degrees out of phase with each other. So the value would then be root 3 smaller than 208 volts. So I'd take my 208 volts and I divide by root 3. Now to get down to my phase value in the load, and I get a voltage of 120 volts in the line as well. So now we have 120 volts per line. We have 12 ohms, trying to keep the math simple. And if we now go to calculate out, I'm just going to erase some of this at the bottom. If I wanted to figure out our phase current, I phase is equal to 120 volts divided by 12 ohms, and that's going to give us a phase current of 10 amps. So 10 amps. So let's erase some of the other stuff here. So we now know that we have a phase voltage of 10 amps. That 10 amps would be seen in all three coils. And if we follow that current with an amp clamp into the line, we see that our line current is the same as our phase current. There is no difference, and that is the rule for in Y, that our phase voltage, our phase current and our line current are the same. And if we continue to follow that current all the way back to our alternator, because the alternator is also in Y, we would find that, and because there's no additional loads added in, we would find that the current drawn at that coil would also be 10 amps. So essentially at this point we've calculated everything except for our three-phase power. So if we were to calculate that out using, let's say, let's do line values at this point. Power is equal to E line times I line times root 3. So we end up getting 208 volts, which is our line voltage, times 10 amps, times root 3. So 208 times 10 times root 3 and that ends up being, so 208 times 10 times root 3, or 1.732, and we get a value of essentially, let me just erase that here, we get a value of 3.60, let's do 603 kilowatts. So that would be the power of our load and also the power seen at our three-phase alternator. I'm going to look at, let's open another one here. Let's look at our delta, and let's look at a Y-connected alternator. And we're going to look at a delta load just to mix things up a little bit for you. And I'm going to stay with the same phase voltage. Actually, let's do something different. Let's do a line voltage of 600 volts. And we're going to do, and this is, I did draw them as inductors, but we'll do it as a resistive load again, just for ease. So we have 600 volts, and we now have a Y-connected alternator and a delta. So that was our alternator. And we have a delta resistive load. We are going to do 15. Oh, that wasn't good. We can take that out. Let's do 15 ohms per phase. Now we have a line voltage, so we need to figure out what our phase voltages are in our alternator and our delta load. And if we have a line voltage of 600 volts, when we go back into the alternator, we see that there are two coils that are producing that voltage to produce the 600 volts. So if there's two coils that are producing them, and they're not 180 degrees apart, they're only 120 degrees apart, so it won't be exactly half of the voltage, but it's going to be root 3 smaller. So if we do 600 volts divided by root 3, we end up getting a value of about 347 volts. It's roughly 346 and change, but we'll do 347 just for ease. So 347 volts for our E phase. So E phase is 347 volts. But when we look at our line value, when we go to come into our delta connected load, we see that this point and this point, no matter where it is, if it's right close to the load or if it's far away, is all the same point electrically. So we do not have two separate loads or two loads splitting up that voltage. That 600 volts is going to be seen across that entire coil. So that means that our phase current, and as to our rule that E phase and E line are the same, we end up having a E phase at our three-phase load of 600 volts. Okay. At this point, we need to now figure out what our line current is, our phase current is, and this is where things can get a little tricky for some people, or majority of people actually, to start out. Obviously, using Ohm's law, we know the defined current is volts. This isn't showing up very well. Let's erase that line. We know that I is equal to E divided by R. So we have 600 volts. 600 volts divided by 15 ohms. And if we pound that out, I believe that is 40. I'll just double check. Yep, 40. So we have 40 amps as our phase current. And here's the tricky part. Excuse me. So we have 40 amps per phase. And I want you to think back to parallel single-phase circuits. And when we would get to a terminal like this, we all understand and realize that we have a split of current. One goes one way, one goes the other way. So if the current is splitting when it comes into the load, it means that the load at this point here, or in the line here, has to be larger if both phases, or all the phases of the load, all see 40 amps. And as well, just like voltage, we are not going to be exactly twice. It's not going to be 80 amps, although that, if we were doing a single phase circuit, we would have 40 go one way, 40 go the other way. But because they're not 180 degrees out of phase, and I'll keep reiterating that, they are 120 degrees out of phase. If we take our current of 40 amps and we then multiply that by root 3, so 4 times 1.732, or 40, times 1.732, we end up getting a, that was a good, get this back, draw. We end up getting a line current of 69.28 amps. So line 1, 2, and 3 would all see 69.28 amps. That current, however, when we end up coming back and follow that current back to our alternator, this is where things end up changing a little bit. Because when we get back to our alternator, we know that the rule for current in delta is different than it is in Y. Once we get back to the alternator, we see that we don't have two completely different coils producing that current. There is just one coil per line. So whatever current is seen in the line is also going to be seen in the current. So we find that the current at the alternator is also going to be 69.28 amps. When we end up looking at our overall power, because we don't have multiple loads, whatever power is seen at the load is also going to be seen at the alternator. So you can calculate power once if you want, or if you want to double check yourself, or just check your answers, you can calculate your power at the load and also at the alternator. And if they both end up being the same, then you likely came up with the right answer. This time I'm going to calculate our three-phase power using phase values again. I want to just bounce back and forth just so that you are familiar with it. Power is equal to E phase times I phase times 3. So in this case, we would use 600 volts times 40 amps times 3 And if we plug that into our calculator, we have 600 times 40 times 3, we get a value of 72 kilowatts. So I'll just write this at the bottom. 72 kilowatts is our total power of the entire circuit. Something I do want to mention to you guys, and I see it fairly often, is a lot of people, when they end up punching something into the calculator, they just assume that if once they hit equals, if the calculator has an answer on the screen, that answer might or must be right. A lot of times students, in the process of pounding them all in, you could have multiplied by mistake when you should have divided, or divided when you should have multiplied. So it is important, before you actually calculate out something, is to kind of have an idea in your head as to what you think the answer might be before you put it in. That way you don't just make the assumption that the answer that's on the calculator is 100% correct. Let's continue on. I don't want to get into too much, just because I'm obviously having to draw these pictures a little bit larger. However, let's do now, let's try and do 2 loads on the screen, both resistive loads, and see if we can fit all that in. I'll try and draw the pictures a little smaller for ease. And we are going to do one of them as Y, and the other one we are going to do as delta. I'll try more and more to not have all the lines in, because they can kind of make things a little more congested with all the lines. Just draw these across the bottom, and we'll try and make this as easy as possible. But let's do a value of at our alternator, and this is load 1, load 2. Our alternator has 100 volts as a phase value, so that would be E phase. And right off the bat, if you're looking at this, we have load 1 is also a Y connected load, so we already know that our E phase here is also 100 volts. Let's pick a value of 5 ohms per phase. I'm only going to do one of the 5 ohms. Just, we're going to say that all loads are 5 ohms, and our delta load is going to be 10 ohms per phase. So if we take our 100 volts, obviously that's what's produced at that point, and we want to go up into the line and look at our line values between here and here. We know that we are root 3 larger, so 100 volts times 1.732 should give you an answer of 173.2 volts. And I'm trying to use my fingernail to try and do things a little smaller. So we have 173.2 volts and the line there. That would also mean that we have the same voltage, 173.2 volts all the way over here. And the rule in delta, as we've already talked about, is that our phase voltage is going to be same as our line voltage. So our phase voltage all the way over here is going to be 173.2 volts. And now we want to break down what the current is per phase. So we're going to use Ohm's law. I'm just going to raise this up here to give a little more room. And to find our current per phase, we have I is equal to 100 volts divided by 5 ohms. And we have so this would be phase current. We'd be calculating out a phase current of 20 amps. So I'm going to just write down here. And when I'm on the whiteboard, I'll kind of show you. I like to put all the values underneath each load. Kind of just keeps all your thoughts and all your answers concise, and you can go back and find them a little easier. We have 20 amps. And we already know we have a resistance of 5 ohms per phase. And now we want to look at phase number 2. So this is of our inductive load. And Ohm's law again. We have now 173.2 volts divided by 10 ohms. And we have a current per phase of 17.32 amps. I'm going to rate my I phase down here, and we have 17.32 amps. The nice thing when you have resistive loads that you will not have when you have a RL, so a resistive inductive load, or a RC or an RLC circuit, is that if all the loads are the same, meaning that they're all resistive, so if they're all resistive, you can add that looks terrible. I need to get used to doing this. Add all line currents. You can just add all line currents together. Okay? But it is important that you're using line currents, not your phase currents. So let's delve into that. Once this question is done, there is a fair bit. I will be stopping the video. If you do want to go back and rewatch it, you can. I will be also posting some information online. But we have a phase current. So our phase current right here is 17.32 amps. We need to figure out what that value is when we get up into the line, or even our terminal current. Once again, remember that the power is produced over here at our alternator, and it is traveling along, and once we get over to the load, a certain amount will want to go down this way. So we have 40 amps that way and 40 amps this way. But because those two phases are 120 degrees out of phase with each other and not 180, we know that the answer must be root 3 larger. So if we have 17.32 amps times root 3, so 17.32 times 732 or root 3, that ends up giving us an answer of 30 amps, and it all depends on your rounding. So we see that at this point we have 30 amps. So that's the trickiest part, and that's where a lot of students end up failing or messing things up, is that they forget to make it root 3 larger when they come out into the line. So this is my I line. Now we want to look at our line current of our load number 1, our Y load. This is where things are easy when they are in Y, because the current that is in that phase, when we come up, we notice that is only one coil that is using that volt current, not like we had in the delta. So we don't have to change the current. We can just bring that value up. So we end up having a current of 20 amps. And we can now, just as I said, and we made that note that you can just add the current. So we have 30 amps from load number 2, 20 amps from load number 1. So that means that the current seen at our alternator, and I'll just do it at the bottom, is 50 amps for our line current. So that'd be I line. Once again, that looks brutal. Let me just make this a little neater. So we have E phase at our alternator is 100 volts, and our I line is equal to 50 amps. Because it is a a Y connected alternator, that 50 amps that is seen here can be brought down into the alternator. If it's delta, we'd have to change it. So we also know, because its I line is 50 amps, and in Y our I phase and I line are the same. So we can also say that our I phase is our I can't even write it down there. Anyways, you can make a note on that. Your I phase is also 50 amps. Lastly, we want to calculate out what our powers are. I've got all the values written down, and from here I'm going to erase everything in the center of the picture, and we'll just stay with our values that we're using. So to calculate out our powers, let's look at, so this was 50, we had 50 amps over here as our line. So the power, we have power at load number 2, power load number 1, and we have power at our alternator. And this is fairly interesting what we end up finding. So we're going to use our let's use phase values because they're all written down. So our phase values, we're going to have E phase, which is 173.2 volts, and we're going to times that by 17.3 amps, and we're going to times all that by 3. So our 3-phase power at load number 2, so 173.2 volts times 17.32 amps times 3 is 9 kilowatts. At load number 2, we have our E phase is 100 volts times 20 amps times 3. So 100 times 20 times 3 is 6,000. So we have 6 kilowatts. So we have 9 kilowatts and 6 kilowatts. So if you're looking at this, the nice thing is, and where I hope you are leading to, is that our total power, because they're all resistive loads, is 15 kilowatts. But we will just calculate that out first. So 15, I got that from the 6 and the 9. Add together is 15. So if we look at 100 volts times 50 amps times 3, and if you pounded that all out, you would get an answer of 15 kilowatts. So if you use your values at the alternator, use your values at load 1, and you use your values at load 2. If you've calculated them all individually and then calculate your powers after that, you can go back and check all your answers. So if the values don't add up like that, it means you've made a mistake somewhere. But if they do, you are likely in the right direction. I'm going to have questions online for you guys, and I'm going to be talking to you guys tomorrow as well. Let me know if you want me to print those off and hand them out to you guys. If so, I do not have a issue with that. So hopefully this wasn't too bad, doing it this way on the iPad and just hearing me rather than seeing me. Thank you for your patience with all this, and I will see you later. All right, have a good day.